meeting right now. So I'm very happy to have this opportunity to introduce my research to the community about the multiscale magnetosphere simulations with MHD-AEPIC model. And so I finished, well, it's still an ongoing work, but I conduct this research with my collaborators, Gabor Tos, Sasha Zhou, Xiantong Wang, and Yuxi Chen. So to start with, here is the idea of MHD and more. So in our field, when we talk about space plasma simulations, it really starts from a MHD description because it's a development of the traditional fluid dynamics model, and we found that MHD is very good at in describing the overall configuration of the magnetosphere, and we have a lot of successful works with MHD simulation, not only in the Earth's magnetosphere, but it's also applied into other space environments like the solar physics or the planetary sciences. But when we get more and more from the MHD, we feel like there's limitations MHD model are with. The major issue is using MHD, we have to assume that the plasma distribution is Maxwellian. Although there are modified MHD models later, but in general, the classic ideal MHD idea is that we have to assume a Maxwellian distribution. And this is not actually true when we have more and more space observations. For example, the newest, not that new right now, but the relatively new MMS observations or even earlier missions reveals that we have non-Maxwellian distributions at a lot of places, especially places related to magnetic reconnection. So in the University of Michigan, we started this effort actually about a decade ago, trying to investigate whether we could improve our model's capability to really embed these physics into the MHD. The global kinetic modeling is very expensive, and I guess nobody right now can afford it. Well, maybe afford 1 or 2 rounds, but at the systematic investigation, we need multiple simulations, and the global kinetic modeling is still very expensive. So then in 2014, Dardov proposed a two-way coupling method trying to put a kinetic region into the global magnetosphere, a global MHD simulation domain. And we use, inside that kinetic region, we use particle in cell model as our kinetic model. And then outside this region, we use MHD to describe the general configuration. And it turns out to be pretty successful during then. And then in 2017, Chen improved it used this model to study the dayside Earth's magnetosphere, the FTEs and the features, kinetic features, and it shows a very good agreement with the observations. But during then, the MHD-AEPIC model, or the MHD with embedded particle in cell model, the particle in cell model can only run on a fixed Cartesian grid, which has a lot of limitations that usually either the geometry or the region of interest is not a box, right? So we're trying to break that limitation by introducing magnetohydrodynamics with adaptively embedded particle in cell model. In this model, we can only apply PIC only where it's needed and when it's needed. And we improved our particle in cell model with, now it's called flexible exascale kinetic simulator, which is called FLEX. I should change this citation here because this paper was just accepted in the computer physics communications. Right, the flex grid is based on the blocks, so it can be turned on and off during the runtime. We also we will not talk about high order scheme in this talk, but in the bus or in the SWMF, we can also do high order scheme. So In this talk, I will mostly talking about the sawtooth event simulation, or geomagnetic storm simulation, and substorm and MI coupling, which is like ongoing work. So to start with, I would like to show this different components of the space weather modeling framework that is keep evolving, developing inside the University of Michigan. So we have different modules to simulate different parts of the space system or the solar terrestrial system. In the red box here shows the geospace model with particle in-cell model. The main part of the model is the MHD model, which is called BASRAS, and it's simulating the Earth's magnetosphere, and we can couple it with different models simulating ionosphere, thermosphere, and here is the particle in-cell model that's simulating the kinetic physics. So to start with, I would like to talk about the magnetosphere simulation under a relatively steady driven solar wind condition, which generates sawtooth-like oscillations. So in this simulation, we still put a box-shaped peak box in the magnetotail from -80 to -6 on the x direction, -20 to 20 on the y direction, and -10 to 10 on the z direction. So we want to keep everything as clear as possible, really to isolate the actual features of the sawtooth oscillations. And here you see a 3D plot of the magnetosphere, and the black box here shows the peak box, and you can see field lines and magnetic field lines in the tail, and you see flux ropes they're generating in the magnetotail. So in this simulation, we mostly using two types of solar wind conditions. One we call it strong driving, another one we call it weak driving. And their major differences are basically the solar wind speed on the x direction. For the strong driving is -600, which is faster, and the weak driving is -400, which is usually the solar wind speed we observe. And also the IMF-BZ for the strong driving is -15 nanotesla, which is also pretty strong. To compare with, in addition to the MHD-AEPIC simulation, we also conduct whole MHD with strong driving and ideal MHD with strong driving. And in the whole MHD simulation, the whole region is the same as the peak region, again, to really isolate the fact that only the kinetic physics here between these two rounds are different. So here are the results of the simulation. One major feature of the sawtooth oscillation is the magnetic inclination angle and BZ perturbations near the geosynchronous orbit. So the panel A shows the magnetic inclination angle and detected from the 4 simulations near the geosynchronous orbit. And here you can see for the ideal MHD model, because the driving is steady and the whole magnetosphere system falls into a steady state. Even the run is time accurate, but the whole system was like going into a steady state. And for the whole MHD, which is showing in the solid gray line here, it has some perturbations, but not a large perturbation that as strong as the sawtooth oscillations. And with MHD-AEPIC run, when we put kinetic physics into the tail, we can also see small oscillations. But when we really look at the red line, we see a very strong perturbations of the inclination angle that drops to sometimes below 30 degrees, which is agree with the observations of the sawtooth oscillations. And so from this comparison, we can see that not only the solar wind condition needs to be strong enough to induce these sawtooth oscillations, but the kinetic physics in the tail really plays an important role here. And also we provided the BZ perturbations near the geosynchronous orbit, and the upper panel is the MHD-AEPIC results, and the lower panel is the polar observation. So here we we're showing the BZ perturbation. Their absolute values are different because we are extracting BZ from a different latitude, but the overall the perturbation magnitude is about 40 nanotesla, which is around which is about the same as the observation, and the period. And the period is about 1.5 hours. It's slightly shorter than observation, but it's still comparable. And we can also see some partial dipolarization features as observed in the polar observation. And also in the observation, we can see this high frequency features is also revealed by the simulation. So when we check the overall feature of the sawtooth oscillations, we go into deeper about how the physics or the physical process of the magnetic tail when the sawtooth oscillations are happening. So we plotted the magnetic field energy and particle energy inside the peak domain. And we can see that there's like periodic loading and unloading feature of the magnetic field energy and the particle energy corresponding to the oscillations when the oscillation is happening. About 10% of the total energy is transferred back and forth between the magnetic field and particles. And the lower panels are showing the electron kinetic energy with the sign of the electron speed on a isosurface plane, which is where the Bx equals to 0. So it most refers to the tail current sheet. So we plotted these two types of magnetotail we see in the simulation. On the left two columns, they're what we identified as stretching phase, which you see like a lot of short and weak isolated X lines, and they're in a distant tail. But when the sawtooth oscillation really happening, we observe this dipolarization phase in the magnetosphere, which you can see this long, strong, and near Earth X line really happening, and this is where the reconnection happens and release the magnetic field energy loaded from the solar wind. Another feature of the sawtooth oscillation is the magnetic local time distribution of the perturbation. So the middle panel is the super post-epoch observation at the geosynchronous orbit. The left panel is the LFM simulation with the outflow, and the right panel is what we get from the MHD-AEPIC. I want to point out that the wide range of the magnetic local time perturbation is reproduced by the MHD-AEPIC. The periodicity is comparable to the observation. The minimum near the midnight is not captured, probably because of the reason that we probably don't have enough. So the outflow here is one reason people think may inducing the sawtooth oscillations, but we are definitely cutting off this source. And so since we can still get the most features of the sawtooth oscillations, so we think that probably kinetic physics is another inducing factor of the sawtooth oscillations. So when we have this MHD-AEPIC simulation, we want to expand our event simulation to magnetic storms. And when we're doing kinetic simulations for storms, there are challenges. Usually the biggest challenge is the storm events usually last for a longer time. So if we use kinetic physics, it may take much longer simulation resources. And also the flapping motion of the tail current sheet is usually happening during a magnetic storm. So we may need a large enough PIC box to cover all the regions of interest, and maybe most of the PIC box, they're not simulating the kinetic physics because of the tail current sheet is keep moving. So we think that the PIC region needs to be adaptive. So we improve this MHD-AEPIC to MHD-AEPIC by introducing this. So this is a schematic plot of the simulation domain. So inside this simulation peak domains. Usually in the MHD-AEPIC, the peak domains are fixed, but in the MHD adaptive peak, we have active peak region inside the peak domain, so this can be turned on and off during the runtime. And we also propose several physical quantities or geometric quantities to find reconnection sites. The first is the geometric criteria to restrict the peak domain into the tail inside the magnetopause. You can use different types of geometric criteria you want, but here we use a paraboloid. And also we try to use physical criteria to find the reconnection sites, because in the runtime, if you want to identify identify the reconnection region, tracing the field line and find the magnetic null point is very time consuming. So we calculate these features from the MHD simulation results and give it to the peak model to decide where we should use the kinetic physics. So the first criteria we're using is identifying the current sheets, which is the J over B perp. And also we use the divergence of the curvature to try to distinguish X lines from O lines. And we use the specific entropy to exclude the solar wind. And we'll keep developing these physical criteria in our model. And now there are more criteria can be used. And also, if you have a specific criteria in the specific problem you're investigating, you can easily customize this criteria into the simulation model and then apply it during your simulation. So, well, here's just a brief introduction to the solar wind condition we're using during this magnetic storm. I would say it's a moderate storm with a minimum DST observed at around minus 124 nanotesla. And solar wind speed stays around minus 600 for a while. And IMF-BZ reaches minus 20 nanotesla during the main phase and stays around minus 10 during the recovery phase. And here is the illustration of the peak region is changing during the simulation. We select like 6 time snapshots during the simulation. The plane here you are seeing is a meridional plane with the current plotted. And the gray iso surface is where the peak region actually is used. So at the beginning, it's tilted with the current sheet, and then it can also capture the kink motion or shape of the current sheet. When the main phase started, you can see it's expanding and capturing more regions of interest in the magnetotail. And here we plotted the volume of active peak region with reference of the DST. So you'll see that the volume is keep changing during the simulation. And when we got the simulation results, we started comparing the runs with kinetic physics with the runs that without kinetic physics. So we started from the global indexes. And here we show the Sym-H and SME indexes, which are corresponding to the ring current strengths and the auroral activities. And all 3 models have good agreement with observation, which is not out of expectation, because the kinetic physics really in the storm is usually behaves in the reconnection region, and the global configuration shouldn't change much. And we also compare with the geotail observation in the magnetotail, and all 3 models give similar agreement with in situ observations. Unfortunately, we captured wrong side of the current sheet from 19 to 22 hours. And we also observed that whole MHD yields usually more high frequency features that is not that realistic compared to the observation. And then we analyzed the flux flow features from 3 different models. The panels A1, B1, and C1 you see is in the meridional cut. So you see this very familiar magnetic field line configurations of the magnetic tail. Since I'm extracting the same magnetosphere at the same time of the simulation. So you see the configurations, they are very similar to each other. And the other panels, they're the B at the B minimum plane to really isolate the features from the current sheet. And the major difference is that in the ideal MHD model, we only see one single big flux rope here. You see a pair of BZ with different signs, and also a strong BY in between as a core of the flux rope. But for whole MHD and PIC, we can see more detailed structures, more mesoscale structures, basically. And away from the tail, you see larger flux rope, and close to the Earth, you see smaller structures. And since we are having kinetic physics, so we also observe, try to observe the electron scale features in the diffusion region. So here we chose 3 points, A, B, and C. A is mostly in the inflow region, C is mostly in the outflow region, and B is where we think is the diffusion region. We also extract a MMS observation from a paper by Huang et al. In 2019, which he indicates that B might be the location of the reconnection frame here. So we extracted at the relatively the same location, and you can see not only the distributions there, the shape of the distribution functions, they are close to each other, but the range of the velocity is also about the same, which is roughly from minus 40 kilometers per second to 40 kilometers per second. And we also examine the inflow feature and the outflow feature of the reconnection site, and we can see that for inflow region, we see the particles, they are usually distributed along the field lines, and for the outflow region, we see a heated particle distributions and with a shifted core of the Maxwellian. So continuing the work.
Time. Sorry, Xiantong, to interrupt. We're just coming up on half an hour.
Okay, so yeah, there's some ongoing work about the BBF propagation in the tail, and we see the BBF propagating to the Earth and with a corresponding current wedge enhancement. And when we analyze the field line current features in the tail from the peak results, we can see this region 1, region 2 sense of field line current. So with this new model, we'll study the MI coupling process in the magneto tail with more informations of the kinetic physics. Yeah, so here is my summary slides. Now I'm happy to take questions.
All right, thank you. So we have time for one quick question. Eric has a question regarding the sawtooth events. So you guys don't have any of the heavy ion outflow in your simulations, but how do you expect the heavy ions might affect the relevant kinetic physics if you guys were to include them in the future?
So I think heavy ions, they're a very important feature in the sawtooth events. The reason we didn't include it before is we try to investigate the kinetic effects. But I think my understanding is that if we include heavy ions into the model, and when it's loading and propagating to the magnetosphere, it will change the composition of the tail plasma, and then it will affect the reconnection rate most likely. And actually, we think that if we include the ions, we may get a better period of the sawtooth, because usually if we have a heavier composition, maybe the reconnection rate will be slowing down, so we can load more energy into the magnetosphere before it gets released. So I think this is it's also a very important factor. I also stated in my paper saying that this is probably accounts for the difference or discrepancy between our model and the real observations.
Oh, okay, very cool. Thank you. So our next speaker is Dr. Chen. Yang, if you would like to take the screen. So Dr. Chen is an assistant professor at the Department of Statistics at the University of Michigan and a research assistant professor at the Michigan Institute for Data Science. She received her Bachelor of Science in Mathematics from the University of Science and Technology of China in 2011, and her PhD in Statistics from Harvard in May 2017. Yang's general research interests are in applied and computational statistics, including Bayesian models and computation, hidden Markov models, and general finite mixture models, as well as the application of statistics and machine learning in astronomy and space science, which she'll be focusing on today. So today I'm happy to have Yang continue our discussion of work on the Solstice Drive Center, highlighting her work on explainable Sym-H forecasting with gradient boosting machines. Yang, if you'd like to take it away.
Thank you, Kyle, for the nice introduction. It's my great pleasure to talk about our Solstice projects here. So today I'll focus on one of the Solstice projects that we have worked on before. But before that, I'll give a very rough overview of a lot of the data-driven problems, data-driven approaches to space weather problems that I have worked on before with my students in the past 4 to 5 years. So we have worked on solar flare prediction problems. So the way that we take it is that we use different kinds of data inputs, such as the sharp parameters and also the HMI-AI images. And then we try to construct important features, physically driven and also purely statistical methods to construct important features. And then we try to predict in advance what is the probability of having a strong flare event within the next 24-hour or 48-hour window. And also we try to predict, given that a flare is arriving, what is the corresponding intensity of the flare. So these two figures are showing that trend. And nowadays, we're actually developing newer machine learning models or new statistical models that combines the idea of tensor construction and Gaussian process modeling and regression approaches, trying to combine information from HMI and AI images, and then try to come up with better binary classification of solar flare events, and also the solar flare intensity. And besides, we have also been working on geomagnetic index prediction problems, and part of that is the Sym-H prediction. And we're also working on delta B prediction for local stations, which I will briefly talk about later on in this talk. And we have been also working on total electron content map completion problems within our group, joined with Professor Shasha Zhou from University of Michigan. So this is the original Madrigal TEC data map, which has a big data back gaps and also noise levels. So we designed a new video imputation algorithm that takes into account of spatial and temporal continuity information to obtain newly fitted global TEC maps. So currently, we are actually publishing our database, and our paper for scientific data has been accepted recently. So stay tuned for the results from our group. So today, I'll be focusing on Sym-H prediction. For this particular group, I don't really have to emphasize too much about geomagnetic storms and why it is important and why we want to work on it, but I still want to briefly review these as the baseline of my talk. So we're focusing on very brief disturbances in the Earth magnetosphere caused by energy transferred from the solar wind. And the largest storms typically result in solar CMEs. And in this particular work, we focus on the Sym-H index, which is a 1-minute resolution version of the hourly DST index. And DST prediction has been in the literature for a while before we even started working on Sym-H prediction. So DST index measures the symmetric geomagnetic disturbance of the horizontal component of the Earth magnetic field near the magnetic equator on the Earth's surface, and it mostly hovers around 0 NT during the geomagnetically quiet times, but during storm times, it can be very extreme. And typically, the standard is that we define a geomagnetic storm to be a moderate storm if the DST index is between -100 to -50 nanotesla, and then define it to be an intense storm when the DST index is between -250 and -100, and define it to be a superstorm when the DST is below 250. So we have different kinds of geomagnetic storms. At solar maximum, we have the ICME storms, which is featured by this super abrupt change and very small, like very extreme DST values. And we also have the solar minimum CR storms. So this particular work, we focus on DST index smaller than -100. So our objective for this work is to obtain interpretable predictions of the Sym-H index 1 to 2 hours ahead of time using a data-driven approach. And then we also try to interpret our results. So here I just want to briefly discuss about what do we mean by interpretable or explainable machine learning algorithms and why we care about them and in what circumstances we want to use them. So most of the machine learning methods, such as neural networks, which is the most famous, convolutional neural networks, residual neural networks, and long short-term memory neural networks are widely adopted in space weather. They are proven to be highly accurate, but they are very complex for us to understand its decision-making process because the neural network comes in layers, and for each layer, there's some nonlinear and linear operations going on. It's very difficult to get through each layer of the neural network to give some interpretations. And this kind of prohibits the use of neural networks in many important or critical applications because it's purely black box. And also, the other thing is that highly accurate, typically for neural networks, especially for very complex architectures, those are super accurate for training sets. For testing sets, it's a problem. So the interpretability and explainability is highly crucial if we want to trust these methods, especially in the super high-risk methods. So especially in space science, we pay attention to the interpretability of these kind of machine learning methods because we want to see if we can verify the model's predictions are consistent with the physical knowledge that we already have. The nice thing about space weather prediction problems is that over the years, we're already standing on the shoulders of the giants. People have already accumulated a lot of experience on what might be important, what is not important, what are the different categories of different types of events, and what are the what are the features of each type of events. So if our interpretable machine learning methods can verify the physical knowledge, that means at least the machine is learning something that the human have proven to be true. And then potentially, we also want to provide some novel insight into the underlying physics. One example of this is that we can try to construct all kinds of combinations of linear and nonlinear combinations of input parameters or tuning parameters or physical quantities as inputs into our machine learning model. And then we can interpret their relative contributions to a particular prediction problem. So these kind of relative contributions can potentially provide really novel insight into the underlying physics about what is driving each, for example, for a geomagnetic storm, what is driving the decay phase or the recovery phase of a geomagnetic storm. So these kind of detailed information can do a lot of favor to us. So in general, in many cases, there exists a trade-off between the accuracy and the intrinsic interpretability. So I have a small figure here, which is roughly showing the trend. So for simple linear regression models or generalized linear regression models, course, for space weather people will say, well, our models are highly complex. There's no way that a linear regression model would work. But actually, for many cases, linear regression models can give very nice prediction results. Maybe the prediction accuracy is only 1 or 2% off from the ones that you get from a super complicated neural networks, but it's highly interpretable. And also all of the assumptions are transparent. You can check, you can validate, or you can devalidate. And also it can have nice extrapolation behavior, in which case super complicated models don't have. So I do feel that linear type of models are not really given enough emphasis yet for real applications. Especially in the cases where you don't have a huge sample size, linear regression based type of models. I'm not talking about simple linear regression. I'm talking about linear assumptions in general can actually go pretty far. And then there's the decision trees, which is the type of model that we're actually working on for Sym-H prediction. And of course, a lot of trees, random forest, and then finally neural networks. So this figure is more for training data sets in terms of interpretability and accuracy. Whether they can extrapolate or can work well for testing data set is another problem about fine-tuning, controlling the complexity of the model and stuff like that. So in general, interpretable machine learning models can be classified as intrinsic. The model itself are intrinsically interpretable or not. So for decision trees and linear regression models, they are intrinsically interpretable. And there are some post hoc interpretable results. So after training the model, we can do some calculation in order to obtain interpretable results. And that's what we use for the Sym-H prediction here. And there's the local versus global interpretable machine learning methods, or in other words, is trying to explain individual predictions versus overall modeling behavior. And there's also the model specific versus model agnostic interpretable machine learning methods. So in this particular work, we adopt a local model agnostic interpretability method called SHAP. It's called Shapley additive explanations to interpret the predictions based on the gradient boosting machines. So next, I'll just talk about those two methods briefly. Gradient boosting machines, or it's called a gradient boosted trees, and of course, is the base is the tree. It's been used super successfully in a wide range of domains. And in a recent publication in 2021, they validated and showed that actually gradient boosting machines can give more accurate results than neural networks for predictions with tabular data. So in the Sym-H prediction problems, we do have tabular data. The intuition of the gradient boosting machine, or in general, the idea of boosting, which is one of the most interesting ideas in statistics in the past decade, or two, is that instead of having a single complex model, we want to iteratively construct simple models that can improve on the previously constructed models and aggregate them to make decisions. So we could have a simple model, maybe a tree, decision tree, or maybe a simple linear regression. And then we take the residual of that model and then train another model that fits the residual. So by iteratively doing this, we're reducing the error of our predictions. So more precisely mathematically, our model looks like this. Again, yi is our response, which is the Sym-H index, and alpha is just an intercept, is the mean values. And then we train it for m different iterations, and Tm is a regression tree. And of course, xi is the predictor, and epsilon I is just a Gaussian noise for this. So it's an additive model across different regression trees. And we want to use the gradient boosting machines that penalize the overly complex trees, as I mentioned, for forest or tree-based methods, similar to neural network models, is very vulnerable to over-parameterization, or in other words, overfitting. We don't want to do overfitting because the extrapolation behavior for overly fitted models are pretty bad. So in order to do this, our loss function at the mth iteration looks as follows. So this is our original predictor. We add a new trait to it, and this is our residual. Yi is our observed Sym-H index. And then we have a penalization term towards the loss function in this term. So the penalization term is a summation of the number of node that you have for the trees, and also the squared error, squared loss, squared quantity of the node weights. So essentially, this is just penalizing over the complexity of the regression trees, so that finally, combining the residual mean squared error and this complexity of the regression trees, we're able to get a nice, clean, small tree structure that explains the residual pretty well. So that's the key idea for this gradient boosting machines. So this is a concrete example that we give. We want to predict a Sym-H index 60 minutes from now, which is 1 hour. And we have a learning rate, and then we make a bunch of decisions. If the Sym-H index is less than -68.5, it's true, we then go to the next decision-making level. If it's false, we go to the next decision-making level. And finally, we move on to the leaf nodes, which are containing the weights. And then it's adding, across all the different iterations, we're adding all of the different trees together. And many of the times, the different input parameters are interacting with each other in this tree structure. For example, here, the BZ is our first layer, and then the EY is in our second layer, and Sym-H is in our second layer. And again, the BZ and Sym-H alternatively are being used as the decision-making process through the tree goes down to the leaf nodes. So this is the basic illustration of the gradient boosting trees. And there are several hyperparameters for controlling the tree complexity that you use: the learning rate, maximum tree depth, minimum child weight, and feature subsibling percentage, and number of trees, which we're using cross-validation to actually choose. So after the gradient boosting machines, we talk about how do we interpret results from the gradient boosting machine. As I mentioned, the tree-based models are interpretable to a certain extent. But in this case, after many iterations, there are many trees, it's very hard to give concrete interpretations of the results already. So what we use is a post hoc, post-model fitting procedure for interpreting the feature contributions for the individual predictions. So this value is called SHAP. So the key idea is that we want to approximate our predicted results using an individual prediction, using an additive individual prediction term. So the ZI is the binary variable indicating whether the feature I is present or not in a particular model. And phi I is the feature contribution to this particular feature I. For example, the predicted Sym-H value being equal to -100, and then maybe the BZ component is contributing -80 to that. So that's already 80%. And then Vx is contributing -10 to that, so that's 10%. So that's the key idea behind the SHAP values. So there are very nice properties theoretically about these SHAP values, which I'm not going to talk about too much. But I want to highlight that actually the SHAP values are highly computationally efficient for tree-based models. For neural network models, it's very hard to calculate the SHAP values because you need to iteratively fit your neural network models. But for tree-based models, there is an algorithm called tree SHAP that can exploit the structure of the trees in order to calculate the shape values in polynomial time instead of exponential time. So this is highly efficient, and that's why we adopted it. So I'm going to show some preliminary results based on Sym-H prediction. We used the different combinations of the features past the Sym-H values, IMF parameters, SolarWind parameters, and several derived parameters, which is supposed to be really important for Sym-H prediction. But finally, this result showed that's really important. We'll see. So we're collecting data from 42 strong geomagnetic storms between 1998 and 2018 for training and testing. We're using the same set of storms as those published in the literature. And we're using a 2-hour history of those derived parameters and 1-hour history of past Sym-H parameters when the past Sym-H is actually included. So that's the persistent part being included. And if we're not including the past Sym-H index, we're passing down a 30-hour history of SolarWind, IMF, and the derived parameters. So this is some brief comparison of the results to the existing method. On the first column, we're showing the results of our predicted quantities versus the observations. The blue one is our predicted quantity, and the observation is the black one. And then on the right-hand side is the prediction results shown by the results given by the LSTM, long short-term memory neural network. If you look into this storm phase and recovery phase, you can see that our predicted results actually follows the observations pretty well. And of course, both beats the persistent model quite a lot. So in terms of interpreting the results, which is the highlight, our more interesting part of our work, is that actually we could look at the percentage contributions of each of those predictors that we have in this model as a function of the observed Sym-H values. So Sym-H values closer to 0, that's our x-axis here, meaning that's around the baseline level. And then for Sym-H values that are super negative, has a very big magnitude, corresponding to the storm phases. So each of those panels is showing one of the predictors. The past Sym-H, that's the persistence part, the BZ, and the net pressure, velocity. So surprisingly, Vx and the rectified electric field are much less important than others. So the rectified electric field is the EY. We were expecting that rho Vx squared to be the most important during the sudden storm commencement, which means around the Sym-H values negative 100 to 0, but the contribution is similar to that of BZ. So you can see that here. These two figures looks very similar, and actually the BZ is having a larger magnitude as opposed to rho Vx squared. And then those quantities, rho Vx squared of Vx and rho has very marginal contributions only for predicting very low and negative Sym-H values. So corresponding here, we have some non-negligible contributions from these quantities for very negative Sym-H values. So this is the case where we're predicting the Sym-H without using the past Sym-H values. So as we can see here, the BZ becomes the most important, the largest contributor, especially for the very extreme Sym-H values. The BZ is dominating, but still the contribution from EY is still very small, which is also another surprise. And then we are actually looking at the 2004 November storm. This is the storm. The prediction is on the blue curve and observation is the black one. The BZ values is the dashed red curve. And on this plot, we're showing the contributions of each of those predictors to the Sym-H prediction. So as you can see, the contributions from the BZ actually follows the observed BZ pattern pretty well in this case, and the contribution of BZ is actually pretty big during the local peaks of the BZ values, which is corresponding to here. And of course, during the recovery phase, the past Sym-H is dominating. So the parts that were not highlighting using any color is the past Sym-H percentage contribution. So only in the recovery phase, the past Sym-H dominates because it's more or less stable. But then before that, the BZ was actually playing a super important role. So we look at the case where we're not including the past Sym-H as part of the predictors. So in this case, again, the BZ is a super important factor for this entire duration of this storm. And also we see a non-negligible contribution from the density Vx and rectified EY. And then, sorry, there's another piece. So after, when the BZ turns positive, finally, for this red curve, the other factors, for example, the Vx, the rho, and rho Vx squared are becoming more and more important at the recovery phase of this particular storm. So we have quite a few of these results on our website. Please feel free to take a look at them. And actually, in our paper, we wrote that is giving us quite interesting information. So part of our ongoing work is on this ground magnetic perturbation forecasting with the Gaussian process. We're focused on predicting this delta BH value. The advantages of our current model that we're working on to get, we already have the code ready. We're proposing this new statistical model to handle those really extreme values and large deviations. And the advantages of the model that we're currently developing is that this can give us a model-based uncertainty quantification. It can be easily extended to forecast for multiple stations at the same time. So I'll just demonstrate it with one illustration. So this is the black one is the raw observation, which is super volatile and much noisier than the Sym-H. And the dashed regions is our prediction intervals. So majority of the time we can cover the observations with our prediction intervals. So our quantified uncertainty is pretty successful in this case. So I just want to acknowledge the support for NSF and NASA for this. And this is the paper that I presented today, led by my PhD student, Daniel Yang, who is just getting his PhD degree within a month. And he's interested in getting a job in a national lab. And in Daniel's website, he has the interactive visualizations of all of the results that I showed just now. Please go ahead and look at it. And also I put my personal webpage here in case you're interested in checking out some of the results that we do in our group. Thanks so much for your attention.
All right, thank you, Yang, for a wonderful talk. That was really cool. We have time for one quick question, simply because I am on the clock today, and I believe Yang is as well. We have a question from Adriana. When you're looking at your data, how do you balance the data? Since there are generally fewer geomagnetic storm intervals than quiet time intervals, do you do anything in order to kind of regularize that data set?
Yeah, that's a very good question. For now, for this paper, we don't really do anything because we're just looking at the storm time. We cut them based on the starting and end time of the storm time. But actually, if you're really wanting to do some real-time monitoring and real-time operational prediction, we definitely want to take that problem into account. That's a very good point. We have been thinking about it, but this paper is very limited to the scope of local geomagnetic storm prediction.
So this paper, you're only fitting storms and no quiet time then?
No quiet times yet.
Okay, yeah. Cool. Excellent. Well, thank you, everyone. Thank you, Yang, again, and thank you, Xiantong, for 2 wonderful talks. I apologize for cutting this off quickly today, but like I say, we're on a little bit of a tighter schedule than normal. So I hope everyone has a wonderful week, and I hope to see everyone next week for 2 additional early career talks. We have one by Nathan Svitis, who's going to be talking about errors in solar wind propagation, and a second by Gonzalo, who will be talking about identifying the magnetopods from soft X-ray images. So I hope everyone has a wonderful week, and I hope to see you next Monday. Bye.
Thank you. Bye.